For the OTEC system, there exist three types of plants that can be built: a closed cycle, open cycle, and combined hybrid system. These plants must be located in warm areas in which cold water is present. That is, look at the oceanic conveyor belt. From the diagram, we can see that areas such as Puerto Rico, the Bahamas, Cuba, and the east side of South America are ideal. These conditions must be present because the OTEC system relies on hot and cold water to generate electricity at all times. Pictured here is a closed cycle system. In this system, the liquid from a naturally gaseous molecule, such as ammonium or propane, is used as a medium. That is, the warm water at the surface, which is present in tropical areas, brings the ammonium to a boil. This happens because it does not take much to bring ammonium to a boil. In nature, ammonium boils at negative 33 degrees Celsius. After that, everything works as predicted. The expanding gas is used to spin a turbine, which powers a generator that creates electricity. Now, the problem is turning the ammonium back into a liquid so that it can be reused. This is where the cold water at the bottom of the ocean comes into play. In these tropical areas, water at the bottom of the ocean can be as cold as 5 degrees Celsius. Therefore, this cold water is pumped through a condenser where the gaseous ammonium is stored after it goes through the generator. Thus, as ammonium gets colder, it brings it closer to its boiling point where it will turn back into a liquid. However, since 5 degrees Celsius is not cold enough to convert ammonium to a liquid at atmospheric pressures, the ammonium must be stored at high pressures. Pictured here is an open cycle system. The idea is similar to the closed cycle system, except that the warm water in the ocean itself is used as a medium. How it works is that the water is pumped into a low pressurized chamber, also known as the evaporator. Once the water is pumped into the chamber, it is turned into vapor because, as pressure lowers, as does the boiling point of water. However, considering that the boiling point of water is 100 degrees Celsius, the pressures need to be quite low in the chamber. So, once the water is turned into vapor, it powers a generator which makes electricity. From there, cold water from the bottom of the ocean must be used to bring the vapor back into a liquid state. Now, the condensed water can either be returned to the ocean or it can be collected and used as drinking water. Clearly, this is a potential benefit, among others, of the open cycle system because essentially salt water is converted into fresh water. The theoretical hybrid system actually combines the open and closed systems. Like the open system, warm ocean water is pumped into a low pressurized chamber where it is turned into steam. However, the steam then is used to bring a secondary medium, such as ammonium or propane, to a boil. From there, the gaseous ammonium or propane is used to power a generator, and the water vapor is turned back into a liquid. As stated, the water is now free of salt, and it would be ideal to pump the water to shore where it could be used to aid neighborhoods, resorts, and farms as seen in the image. Here are some advantages and disadvantages of the OTEC system. 1. As one can see, OTEC is a renewable energy, which is always a positive when combating climate change. And 2. The fresh water that is obtained from the plant could be used for refrigeration, coolant, and irrigation, which could prove to be useful in tropical areas. However, OTEC cannot be used at large scales, similar to how fossil fuels such as coal and natural gas are used today. These plants can only be built in select areas of the world and cannot be heavily relied on because of the rough environment the ocean poses. Therefore, OTEC can only help offset and not completely replace current energy sources and other renewables which have the potential to be used at large scales.
This French physicist was the first man to develop the concept of tapping thermal energy of the ocean. This is when OTEC began. Georges Claude was a student of Jacques-Arsène d'Arcenval. He built an open-cycle OTEC system at Matanzas Bay, Cuba in 1930. This created 22 kilowatts of electricity using a low-pressure turbine. He created yet another open-cycle OTEC system in 1935, this time off the coast of Brazil, that was aboard a 10,000-ton cargo vessel. Unfortunately, both of these plants were destroyed by waves, and Claude never got the opportunity to manufacture yet another one that produced net power. In 1979, the first closed-cycle OTEC, creating 50 kilowatts of electricity, was built at the Natural Energy Laboratory of Hawaii Authority. This was known as the Mini OTEC, attached to a U.S. Navy barge. This specific plant incorporated cold water pipes and created 52 kilowatt electrical of gross power and 15 kilowatt electrical of net power. There were two laws that were created to promote the OTEC technology in 1980. The first one, Ocean Thermal Energy Conversion Act. This act provided the National Oceanic and Atmospheric Administration the authority to license the construction, ownership, location, and commercial operations of OTEC facilities. The other law that was created in 1980, Ocean Thermal Energy Conversion Research, Development, and Demonstration Act, was a bill that helped to establish within the Department of Energy an accelerated research and development program to foster the early use of ocean thermal energy conversion facilities. In 1981, Japan manufactured a shore-based OTEC plant in the Republic of Nauru in the Pacific Ocean. This plant used cold water pipe with a depth of 580 meters on the seabed. Magnificently, this plant exceeded the engineering expectations, creating 31.5 kilowatt electrical of net power during constant tests. The most recent open cycle OTEC was created in May 2003, producing 50,000 watts of electricity, which exceeds Japan's 40,000 watts of electricity record. This plant can be found off the coast of Keyhole Point, Hawaii. Since 1881 to now, many different developments have been created, each contributing a little bit more to the next development. Today, further research is done in hopes to create more cost-efficient, high-tech turbines for open-cycle OTEC systems to help sway our energy sources from foreign and domestic fossil fuels.